Welcome back. So let's get going on chapter 4. We're going to move on to talk about prime numbers and a little bit more like that. So that's actually what we're going to start off with. Let's just talk about some basic definitions of prime numbers because we're going to deal with some theorems um, that I think you might find a little bit interesting. So first off, let's let n be any integer. If a is an integer such that a divides n, then we call a a factor. If n is an integer in the natural numbers, so that's anything from 0 to infinity, and n has exactly two positive factors, namely 1 and itself, then n is prime. And if n is bigger than 1, if n is bigger than 1 such that n is not prime, then it's called composite. So it has to have exactly two distinct different positive factors. With that in mind, here's your first question that you have to deal with on discussion boards. Is 1 a prime number or composite? Explain why or why not. I just want your opinion on them. 2, I want you to find the first 10 prime numbers. In part because of the process of doing that, how difficult is it? This is really hard. And this leads us to this wonderful lemma right here, which actually is a really cool lemma. Let's let n be a natural number greater than 1. Then n can be expressed as a product of primes. That is, it can be written as where n equals p1 times p2 times p3 through pk, where each p1 through pk is a prime number, not necessarily distinct. In other words, there could be p1 and p2 could be the same prime number and so forth. And this gets us into the idea of what's known as prime factorization that we will get to later on. But this lemma is kind of a really big thing that lets us leverage and do a lot of different things. So, and I'll talk about this a little bit later on, but this lemma kind of opens up a lot of doors. Now, after talking about prime numbers, part of the reason we talk about this is then to go into what's called the greatest common divisor. Suppose you have two integers, m and n, then their greatest common divisor, the GCD, of them denoted GCD parentheses mn, is the largest positive integer that is a factor of both them. And if the greatest common divisor is 1, then they are called relatively prime. That's really important. There's a lot of number theory and a lot of discrete math concepts that are built on, are they relatively prime or not? If they are, then great, we have all sorts of problems. If they're not, then so whether I say something like the greatest common divisor is 1, or I said they are relatively prime, that is the same exact statement. All right, so let's talk about finding greatest common divisors. So if I gave you this is the third problem I've asked you so far to do. So first, go back. Find, is 1 a prime number or not? Explain your answer. 2, find the first 10 prime numbers. And then 3, find the greatest common divisor of 54 and 72. I'm curious to see you show how you found it, because this is the idea, because most people try factor trees and so forth, which do work. However, they are highly inefficient. And finding the greatest common factor is actually one of the best ways, is actually use this in our next theorem that we'll get to in just one second. And it's namely this lemma, that mn, let mn be integers such that m and n are relatively prime. And there exists an s and t such that n times s plus m times t is equal to 1. In other words, there is a linear combination of m and n that's equal to 1. That is a critical idea about relatively prime that's really useful and powerful. All right, go back just real quick. Again, this is a problem I want you to do. It's just a to-do. Provide an example of two natural numbers that are relatively prime. Preferably not prime themselves. That's boring. Find something that are not prime that are relatively prime. All right, let's go back to this lemma. How would we prove this? Well, this lemma is often proven using some very different strategies. So one of the first strategies that's usually used is actually to essentially do what's called Euclid's algorithm, in case you haven't seen. So Euclid's algorithm is where, let's say I have two numbers, I have m and n, and we'll let m be bigger than n without loss of generality. So then we can write M is equal to Q1 times N plus R1. But then N is equal to Q2 times R2 times R1, excuse me, plus R2, where in this first case, R1 is clearly less than N and bigger or equal to 0. And in here, R2 is less than R1. And we can keep doing this process where we do now R1 equals Q3 R2 plus R3. And R3 is less than R2. If we keep going on down, we get Rn plus 1, sorry, Rn minus 1. Minus 1 is equal to Qn plus 1. It's always 2 bigger, times Rn plus Rn plus 1. And then the final line would be Rn is equal to Qn plus 2 times Rn plus 1. Meaning this goes into that Rn right there. And so by doing this process, we actually can work our way back. If they're relatively prime, then notice that R1 is a factor in Rn. Rn plus 1 is a factor in Rn, which is a factor and so forth. And pretty much it comes down to the fact that Rn plus 1 has to be 1 in order for them to be the greatest common factor. This is using the Euclidean algorithm to prove this. And we can suppose it's not, and that's where we get a proof by contradiction. So this proof, I'm just doing a very sketch of it because it's actually really lengthy. Most books I've seen it in, it takes up over a page. It is really nice, and the idea is that there is a linear combination. You can claim there's not a linear combination. Again, you can prove that that's where this comes out. There's a lot of things, but this Euclidean algorithm is actually where it comes in. And that's also useful because that's actually one of the great ways in which we can solve stuff. So I'm going to show this is how the Euclidean algorithm can actually be used to solve things like this. I want to solve the S and T where this is true. One thing you could do is you could guess it. Well, the other way to do this is simply, let's just do exactly what we just had a second ago. So I'm actually going to get a fresh whiteboard. All right, hopefully you're still there. It had a weird glitch that I wanted to talk about. So let's just go through the problem. So I have 2s plus 7t is equal to 1. So the way we solve this, I'm actually going to break it up. Change my color real quick. I actually don't like that green. I want it black. All right, so if I'll start with 7 equals 2 times 3 plus 1, like this. And you'll quickly notice that I can rewrite this then as 7 minus 2 times 3 is equal to 1. So that means 1 times 7 plus negative 3 times 2 is equal to 1. So S equals negative 3 and T equals 1. Now, this is one example of how those linear combinations would work, but it's not the only number that we get actually with here. So another example might be 2 times 4 plus 7 times negative 1 is equal to 1. So again, we had a different S, 4, and a different T. So again, that theorem, that lemma only told us there exists one, not what it really was. All right, let's go back to the other thing. So we solved this problem by doing the extended Euclidean algorithm. It was a very small example, but we can do much larger examples and keep working on it. Now, this theorem, this lemma, is actually going to be a really, really big one we're going to depend on. This is Euler's lemma. And we're going to assume that P is a prime number. And if P divides A times B, then where A and B are some natural numbers, then either P divides A or P divides B. The proof of this is actually a proof by contradiction. And this is where we start seeing a lot more of these proof by contradictions that pop up again and again and again. Again, to show this, I'm just going to switch to a whiteboard real quick. So let me switch that. All right, so let's prove Euclid's lemma. So Euclid's lemma, we are going to suppose that P is the largest prime such that P divides AB. I should say largest is the smallest. My fault. Is the smallest prime. So we're just gonna suppose that let A and B be two numbers and P be the smallest one that breaks this rule. Now the reason for that is I'm going to show that if it's not true for P, but it's true for all prime numbers smaller than P, then we have a problem. So P does not, and P does not divide A, and P does not divide B. Well, since P divides AB, there exists a K in the integers such that KP equals AB. Well, we know that P is prime. And so if the greatest common divisor of A and B is not 1, then we got some problems going on here. So K clearly divides P. And we can kind of go, hang on, let's go from there. Let me pause this for. All right. So again, we have a K. We know that K has to be between 1 and P, because otherwise AB is bigger, then we're going to have a problem. So it's clear that this has to be true, since K times P is equal to AB. Otherwise, P is bigger than the product, and that doesn't make any sense. So, because it can't divide them. So by definition, we have to do this. And then in addition to this, we can say that K is not equal to 1, because if K is equal to 1, because if K was equal to 1, notice that would mean that, let me write that down. If K equals 1, then P equals AB, but that's a slight problem because that means that A and B, which are integers, both go into P. So either one of them is P or one of them is 1, but that's not possible by what we have. So we have a major problem. So we have this whole idea that we're trying to break. So if it was equal to 1, we can throw that out. So let's let Q be a divisor of K. Now, K could be prime. I don't really care. I'm just saying let Q be some prime divisor of it. So then by definition, Q divides AB. But by the minimalist idea, since P was the Qest, I should say this is prime divisor. Q divides these, but since P was the smallest, then Q divides A, or I should say or Q divides B. It's because we suppose it was smallest one that we can work it into. So let's then Q goes into K and it goes into one of them. So we get the equation. We essentially can rewrite this then that dividing whatever value. So if Q is equal to, I don't know, JK, because obviously, sorry, QJ is equal to K. Yeah. And Q divides A, then we can find the greatest common divisor and break these down a little bit further. That's the point, is simply that I can break them down further. And so I can then from here obtain, so I can write, so K prime P equals A prime B prime, where 1 is less than or equal to K prime, less than or equal to K, 1 is less than or equal to A prime, which is less than P, and 1 is less than B prime, which is less than P. So because of this, I can break this down even further to make them all smaller, but this contradicts the primality, and we can keep repeating this process, by the way. We can keep doing this until we arrive at the fact that some K, the only K that's left is K is 1, and that means that P is not prime. So that's how we kind of keep, we repeat until K, repeat until K star, K double prime equals 1. This contradicts the primality of P. So we get this problem and we get done. Hopefully that makes a little more sense. So this theorem is really cool because if P divides some product, then it has to divide at least one of those factors in that product. And that's all it says. And this is why it's super powerful. So I want you to find this answer, and that is provide an example of integers A, B, and D, where D divides A, B, but D does not divide A and D does not divide B. Notice I didn't say prime. That's kind of the critical component here. So find an example of these things so it breaks these ideas. All right, that's it for this first discussion board. Hopefully let's get you started, get your feet wet, get in, kind of work with prime numbers, and look for some different things. Let me know what questions you also have on the discussion board.